For Fundamental Chemistry 1, we're going to start with Chapter 1, which includes methods and measurement. The learning objectives that we want to cover in this first chapter is working with conversions. Now, conversions are used all throughout scientific study. We're going to be using them through the rest of the chapters during the semester, so it's very important to become comfortable with conversions. This is going to include temperature conversions, going from Celsius, Fahrenheit, and Kelvin. Also, metric American conversions. So this is English to metric and back again. Also, metric to metric. And for metric to metric conversions, we're going to be using prefixes. And you'll see that as we move on through the chapter. We also want to be able to work successfully with significant digits, also termed significant figures. Because when we're reporting our answers after we do the conversions, we want to make sure that we're reporting them with the correct numbers involved. We're stopping when we need to stop, and we're not including any unnecessary non-significant digits in our answer. In this, we're also going to learn rounding. Now, you probably already know rounding, but it can get tricky in some cases, so we're just going to briefly cover that as well. Lastly, we want to be able to define and recognize the difference between chemical and physical properties. We're also going to look at the definition of elements and compounds as well. We're going to start by looking at some units of measurement. And if you're following along in your book, we're looking at Chapter 1, Section 3. English units are most commonly used in the United States. We use feet, pounds, etc. Most other countries, however, use metric units. So metric units are the meter, the gram, the liter, so on and so forth. So in order to share our information in the math and science fields, there was a standardization that was needed because we have the United States using English units and we have most other countries using the metric units. Well, if we want to share our data, our research with each other, we needed a common unit to agree upon so that when we're sharing that information, it's standardized. We don't have to do all of these conversions to figure out what the other person did. That's why people in the science fields, even in the USA, use metric units, is because that is what was decided upon. So the metric units, or the system decided upon, is also known as the SI system. And this is for the System International. So there are 4 fundamental physical quantities and corresponding SI units listed below. So in length, we're going to use the meter. For mass, we're going to use the kilogram or gram, which is most often used in chemistry as gram, not kilogram. For time is seconds. Now that one we're used to. We use seconds here as well. And then for volume, we're going to use the liter. Shown here is the prefix table for metric units. So as we saw on the previous slide, metric was the decided upon SI units, meters for length, seconds for time, grams for mass, so on and so forth. So since metric units were decided upon, we need to know what their prefixes are and also their decimal equivalents, which is listed in this column shown here in red, and their exponential expression. So I just wanted to introduce this table to you now. We're going to go through it in more detail later on in the chapter and discuss how to use this table to come up with some conversion factors. Now you can see in this table the highlighted prefixes, so highlighted in pink here, mega and kilo, and then also highlighted in blue. These are the most commonly used. Okay, now you've probably heard kilo, for instance, kilogram, kilometer. Also centi, you've heard of centi before as well, centimeter. Milli, milligram, most medicine is measured in milligrams. Okay, so that's metric as well. So we will revisit this table and talk about how exactly we're going to use it in our conversions later on in the chapter. Before we get into doing conversions, we first need to talk about significant figures and scientific notation. This is Chapter 1, Section 4 in your book. So what exactly is a significant figure? Well, significant figures are the information-bearing figures. What that means is they're the important ones. Oftentimes, I have students ask me when they're doing a word problem or a mathematical problem, how far out do I need to go? Because a lot of these problems are going to have several decimal places. They might go out 5 decimal points, 10 decimal points, and we don't need to report all those numbers. So in order to answer that question, in order to figure out what numbers you do report, how many decimal places you do go out, you need to use a set of rules to figure out which numbers are important, which numbers are significant. And we'll go over those rules that we're going to be using when doing calculations and word problems. You also need to be aware of significant figures when you're doing measurements. So whether you're doing measurements with a ruler or a beaker or a graduated cylinder. So the rule when you're physically measuring something yourself, whether it be length, volume, time, is that you always want to go one digit further, so one more digit, than the device allows. So what does that mean? Well, this example here, we have a pencil being measured with a ruler. Now looking at this ruler, it has hash marks that go out 1 decimal place. So this would be 0.1, 0.2, 0.3, so on and so forth. So what this ruler does is it goes out to the 0.1 spot, 1 decimal place. Well, we just said when you're measuring physically with a device, you want to go 1 more digit than the device allows. So since the device goes to 0.1, we want to go 1 further than that. So instead of going to the 10th spot like the device does, we're going to go to the 100th spot. So to measure this pencil, I'm going to go to the very tip of the pencil and I'm going to follow it down. It's not going to be a very straight line. So what that means is it looks like it's around 9.5, right? But what we want to do is go 1 further. Is it exactly at 9.5? Well, if it is, then you want to report 9.50 because we need to go 1 further than the device allows. Maybe you drew your line and it's a little straighter than mine and you think it's not quite 9.5. It's a little bit smaller than the 9.5. Well, in that case, then you would estimate where exactly it is. So you think it's not right at 9.5, but a little bit less, so maybe you think it's 9.49. So that's how we're going to use that significant figures when we are measuring physically. And we'll do a few more examples of this as well. Let's first talk about how to recognize significant figures when you're just looking at the number. So if you're looking at a word problem or a calculation problem of any sort, how do you tell how many significant figures the number in front of you actually has? Because this is going to be important in figuring out how many significant figures you need to report your answer in. So rule 1, all non-zero digits are significant. What that means is, if it's not a 0, it matters. Okay, so 1, 2, 3, 4, 5, 6, 7, 8, 9. You see any of those digits and they count. Rule 2, the number of significant figures is independent of the decimal point. Okay, so what that means is if I have 73.1, well, looking at this, they're all non-zero numbers, right? 7's not a 0, 3's not a 0, and 1's not a 0. So that means there are 3 total significant figures. Now, if I were to move that decimal point, so instead of being between the 3 and the 1, and now I have it between the 7 and the 3. Did that change my number of significant figures? No, it did not, because it doesn't matter where the decimal point is because they're all non-zero numbers, so they all count. Rule 3, zeros that are between non-zero digits are significant. Okay, so now we're getting into the harder rules. If it's not a 0, it counts. But what if you have a 0? Okay, well the trick with zeros is sometimes they count and sometimes they don't. So these next few rules are going to tell us when they count and when they don't. So number 3 is saying if the zeros are between two non-zero numbers, they count. So in this example here with 60.053, well, we know the 6 counts, the 5 counts, and the 2 counts because they're all non-zero numbers, so rule 1 applies there. But now we have 2 zeros. To figure out if they count, let's reread the rule. Zeros between non-zero digits count. So, since these 2 zeros are between a 6 and a 5, 2 non-zero numbers, they do count, and we have a total of 5 significant figures in that number. Now let's look at number 4. Number 4 is telling us that zeros at the end of a number are significant only if a decimal is present. So let's look at the examples to clarify this rule. So say you have the number 10,000. There is a comma in the number, but there is no decimal point. All right, so the number 1, does that count? Yes, it does, because it's not a 0. But to figure out if these zeros here count, we have to look and see. Well, rule 3 says if they're between 2 non-zero numbers, those zeros will count. But they're not. There's no non-zero number here. There's nothing, right? Rule 4 says that these zeros can count only if there is a decimal present. There's a comma, but there is no decimal. So that's why the number 10,000 just has one significant figure. All right, moving to the next example, we have 10.100. Okay, so we know that the ones both count, so we're up to 2 sig figs now. To figure out if the zeros count, we have to apply the rule. Rule 4 says that zeros count if there's a decimal point present. Is there a decimal? Yes, there is. Okay, so that means all the zeros count. It doesn't matter if they're at the end or in the middle. They count because the decimal is there. So this has 5 total significant figures. Now let's use the example from before, just 10,000. Okay, well if I want those zeros to count, they didn't count originally over here because there was no decimal point. So if I want those zeros to count, all I have to do is tack a decimal point on at the end of the number, and now those zeros count, and we have 5 total significant figures in that number. The last rule, rule 5, zeros to the left of the first non-zero digit are insignificant. Okay, so we just said zeros at the end of a number count if there's a decimal present. Okay, now that applies only if those zeros are at the end of the number. So in this example, number 5, we have 0.000024. Okay, well, none of those zeros count. Why? You think they should because there's a decimal point. The thing is, though, we can't start counting until we get to our first non-zero number. So I have to skip all those zeros because I can't start counting till I get to my first non-zero number, which in this case is a 2. So the 2 counts, the 4 counts, and I only have 2 significant figures. Up here in this example, when we threw the decimal point in, we said that now the zeros counted. Well, why did they count here? Because we started counting at the 1. That's our first non-zero number, so since we started counting at the 1, all zeros after count because of that decimal. This is a little tricky, but we'll do some practice and get the hang of it. So now let's look at significant figures when doing measurements. So we discussed this briefly and haven't done any examples yet. So with measuring, whether it be length, volume, time, we always want to go one past what the device we're using allows. So the first thing we need to do is look at how far out the device goes and then guess one further. So in this first example with the ruler, we have a piece of felt or fabric being measured. what we need to look at is how far out does the ruler go? Well, the ruler goes out to the 10th spot, right? It goes out 1 decimal place. So when we're figuring out the length of this piece of fabric, we want to go 1 further than what the device allows. So we're not going to go out just to the 10th spot, we're going to go out to the 100th spot, 2 decimal places. Right? So when I was doing this measurement or looking at it, I guessed that it was 1.38. Okay, because we have 1.1, 1.2, 1.3, and then notice that piece of fabric isn't quite at the 1.4 yet. And so I guessed it was 1.38. Now your guess might have been 1.37 or 1.39. That's because this last digit is that uncertain digit that's going to vary from person to person depending upon who's doing the measuring. Let's look at measuring volume. So here we have a beaker. Now looking at it, how many significant figures does the beaker go out to? 20, 30, 40, 50. Okay, well let's use our identification of significant figures and see. Looking at this 20, does the 2 count? Yes, it does. Does the 0 count? No, it doesn't. Okay, because remember, zeros can't count unless there's a decimal point present. So there's only 1 significant figure that the device goes out to. And we want to go 1 more than the device allows. So when we guess how much is in here, when we're doing our measurements, we want to go to 2 significant figures. Device goes 1, we go 1 extra, which would be 2. So when I'm doing this measurement, it's somewhere between 40 and 50. I guessed 43. You might have guessed 44, 42. Okay, once again, that last digit is that uncertain digit. Let's do 1 more. Measuring a paper clip. So this time we have a ruler once again. However, notice that the ruler isn't as precise as the one above. It doesn't have dashes going to the 10th spot. So this ruler only has 1 significant figure. So when we report our answer, our measurement of that paper clip, we're going to go out to 2 significant figures, 1 further than the device allows. My estimate was 2.3. Yours might have been slightly different. The 2, though, however, should be the same between everybody. It's that last digit that might vary. These significant figure examples we're going to look at during class period. So we'll be doing these on the whiteboard. If you are opting out of coming to class, you can watch the videos to see the answers on these as well. So for these examples, we're just going to go through and using our previously discussed rules, figure out how many significant figures are present in each of these numbers. More significant figure practice as well that you will see on the video or during class period. Now we're going to talk about the difference between accuracy and precision. So you saw a moment ago me talking when we were doing those measurements. I said that that last digit was uncertain. So let's define exactly what uncertainty is. So uncertainty is just the degree of doubt. And when you're doing measurements, whether it be with a ruler or in a graduated cylinder or some other device, there's always some error. There's always some uncertainty. There's always some degree of doubt. And that is dependent upon the measuring device and then also the person measuring. With accuracy and precision, we're going to look at the difference between these two and do some examples with that as well. So accuracy is the agreement between the true value and the measure value. So it's how close you are to the correct answer. If you are doing darts, did you hit the bullseye every time? If you did, you are accurate. For precision, it's not necessarily how close you are to the answer or how close you are to the target. It's more how reproducible are your measurements? How reproducible is your throw? So once again, going back to the dartboard, are you hitting the same spot every time, but it's nowhere near the bullseye? Well, in that case, you are very precise because you are getting the same spot every time, but you are not accurate at all because you did not hit the right answer or get the correct result. Let's address error. So error is the difference in the measurements or expected value from the true value. So how close were you to the desired results? We're actually going to be calculating percent error during lab period quite often, where we're going to actually figure out the percentage of how far we were off from the actual values, or what we should have gotten. Now, random error is a type of error in which values are random. Okay, so random error is something that you would see in lab quite often. It often depends upon the ability of the person doing the experiments and how familiar they are, or how closely they're following directions. So multiple measurements can be averaged out to get rid of random error. So you'll often see during lab period we're going to be doing several trials, which means we're going to be doing the experiment several times, or the measurement itself several times, because what we're trying to do is reduce the random error. The more times you do it and take the average, the better your results are going to be. With systematic error, these are values that are consistently off. In systematic error, it's in the name, system. It's usually the measuring device that you're using. So for instance, if you're using a scale that hasn't been calibrated correctly, it's going to be giving you a false mass. But it's going to be off by that amount every time. And that can be corrected just by having me calibrate the machine. So continuing on with error and measurements. So looking at these bullseyes, we're just going to describe them based off of their accuracy and precision. So this first one, notice we have the X's all over the place. Okay, well, it's not accurate because it's nowhere near the bullseye except for this one here. And it's not precise, so very low precision, because remember, precision is getting a grouping, so hitting the same spot every time, even if the spot isn't accurate. Looking at the second one. In this one, we have a very small grouping, so we're hitting the same spot over and over again. That means our precision is very high, because we're getting the same spot. However, the spot we're hitting is the bullseye. So there we have low accuracy. The next one, this one can be open to interpretation. So we're hitting close to the bullseye. It says accuracy is high because of that, because accurate is getting close to the correct answer or the desired result. I would say it's moderate because they're not hitting the bullseye every time, they're just near it. The precision in this case is going to be low because they're not hitting the same spot every time. They're just hitting all around the bullseye. Then the last example is both accurate and precise because they are getting the desired results over and over again. So next I'm going to have you look at these, take a moment, and figure out whether they are precise or accurate. So describe them in terms of precision and accuracy. We're going to do an example like this in class as well, but we're going to do it with data results to describe if they are precise or accurate. So in this first one, we have a small grouping, but nowhere near the bullseye. This next one, we once again have a small grouping, but it is in the bullseye. Next, scattered about, but they're all within the bullseye. And then the last one, they're just all over the place. So the first one is going to be low accuracy because we're not hitting the bullseye, but high precision because they are grouped. Second one, high of both. We're in the bullseye and we're all hitting the same spot. Next one, high accuracy and low precision. Now if you would have said moderate accuracy, that would have been fine too. The last one, neither, right? It's all over the board and it's not on the bullseye. So to reiterate the definitions, precision is going to be reproducible, where you're consistent. You're getting the same results over and over again. Then accuracy is how close you are to the correct. So now that we know about significant figures and random error, let's look at calculations and how significant figures are going to apply when we're doing word problems and other calculations. Now the answer to a calculation cannot have more significance than the data collected in the measurements. What this means is we're going to be using the numbers or the data collected to figure out how many significant figures should be in our answer. So there are some rules. When you're approaching a problem, you need to first look at what type of operation you're applying. Are you doing multiplication and division? Or are you doing addition and subtraction? It is important to note which one you're doing because there's a different set of rules for each. For multiplication and division, your final answer is going to have the same number of significant figures as the data involved. And you want to pick the one with the least number of significant figures. For addition and subtraction, you're looking at the decimal place only. Once again, you are using the least number of significant figures. So the thing that's in common with both is that you're using the least number, so whichever one has the least number of significant figures. But what's different about the two is when you're doing multiplication and division, you're looking at significant figures as a whole. You're counting all the significant figures in the numbers involved in the problem, and you're picking the one with the least amount of numbers, or the least amount of significant figures. For addition and subtraction, you're not looking at significant figures as a whole. You're looking at just the spaces after the decimal point. Let's do some examples to When we are doing these problems and figuring out how many significant figures, we're oftentimes going to have to round. So rounding, you might need to round up or leave the number as it is. So the general rule, as I'm sure you already know, but let's review anyway, that if the number is 5 or more, you're going to round up. If it is 4 or less, you are going to keep the number the same. Now make sure that you are waiting to round until the end of all the series of calculations. So let's start by looking at some of these examples. How many significant figures should the answer have? So the first thing you want to do is figure out what order of operation that you are applying. In this first one, we are multiplying. So since we're multiplying, we're looking at significant figures as a whole. So we're going to take both the numbers involved, 3.67 and 2.123, count how many significant figures is in each, and then pick the one with the least, is what the rules were telling us. So in this first number, 3.67, how many significant figures? There is 3. How do I know that? Because they're all non-zero numbers. Okay, looking at the next number, 2.123, how many significant figures? There are 4 because all of them count because they are all non-zero numbers. So now what I need to do is pick the one with the least. So what number is smaller, 3 or 4? 3. It's an easy one. So that means when I report my answer, I'm going to report it with only 3 significant figures. So when I multiply that out, I'm going to get a big long number. This is what's going to show up on my calculator. What I need to do is only keep 3 of those. So this is where rounding comes into play. So I want to keep the 7, and the 9, because that's 1, 2, 3 significant figures. That's where I want to stop. But when you stop, always look So I'm stopping at the 9, so I'm going to look at the number next to it. The number next to it's a 1. Since it's a 1, that means I'm going to leave this as a 9. So my answer is going to be 7.79. If that 1, for instance, was a 5 instead, then I would have to round up. 5 or higher you round, 4 or less you keep the same. All right, let's look at the next problem. First off, we are dividing. That's what that slash means. So we're once again looking at the total number of significant figures. So I'm going to go ahead and count them. This first number, 1.52, has 3 significant figures. Dividing it by 2, that's just 1 significant figure. I want to pick the smallest. 1 is smaller than 3, so that means my answer should only have 1 significant figure. When I do that division, the answer showing up on my calculator is in 2 significant figures. I want just 1, so 0.7, that's 1 significant figure. I'm going to stop there, but always look at the number next to it. The number next to it being a 6. Since 6 is 5 or higher, we're going to take that 7 and round up to get an answer of 0.8. Next, we have addition. So with addition, remember this is different than multiplication and division. Okay, because now we're not looking at significant figures as a whole, we're just looking at about how many places after the decimal point. Okay, so decimal only. So counting decimals only, this first number, I'm going out to 3 decimal places. The next number, how many decimal places? So I'm not paying attention to this 2,112. No, I'm looking at just after the decimal. So I start at the decimal and there are 2 decimal places. Next, 25.00. Just after the decimal point, there are once again 2. It doesn't matter that they're both zeros. We're just looking at how many spots are present after the decimal place. 3.1, there's just 1 number after the decimal point. So just like with multiplication and division, we're going to pick the least, the smallest number. The difference is we're looking at just the decimal places, not the numbers as a whole. So looking at these, I got 3, I got 2, 2, and 1. So 1 is clearly the smallest number. So what this means is when I report my answer, I'm going to go out 1 decimal place. That doesn't mean I'm going to have 1 total significant figure, it just means I'm going out 1 decimal place. So let's see how that looks. So when I get the answer, I get 2,140.355. Okay, so we just said we want to go out 1 decimal place, so I find my decimal point and I'm going to underline the number that comes after it. In this case, it's a 3. That's 1 decimal place. I stop there, but I want to look at the number next to it, which is a 5. Since it's a 5 or higher, I'm going to round that 3 up to a 4. So my answer is 2,140.4. So it's a total of 5 significant figures, but notice I only went out 1 decimal place. So that's the difference between addition, subtraction, and multiplication, division. So here are some more examples that we're going to use to practice during class period to kind of get a handle on this. So we'll review the rules and do some problems together in class. If you are opting out of class and doing the online, you can watch the class video to get those answers and check them with your work. So here's for rounding. Okay, so we're going to do some practice with rounding. And we'll do this on the PowerPoint, not during class. So what this question is asking us is to round to 3 significant figures. Now most people think rounding is pretty easy, but it can get quite difficult. So that's why I wanted to do some examples. So that means we want just 3 total significant figures. When you're counting significant figures, you always go from left to right, just like reading a book. So in this first problem, 61.40, I'm going to start at the 6. So that's 1 significant figure. The 1 will be 2. And then this 4 will be 3. So I'm going to look at the number next to it. It's a 0, so that's going to stay a 4. So 3 significant figures will be 61.4. Let's try the next one. Same thing. We want 3, so we start at the left. So 4, 4, and 1. So I'm going to stop there, but I always need to look at the number next to it in case I need to round. Do I need to round in this case? I do. I need to round that 1 up to a 2. So now I have 3 significant figures. Now here's a tricky one. So we have to apply our rules of significant figure counting. Does this first 0 count? It does not. Does this second 0 after the decimal point, does that count? No, it doesn't. Why? Because even though there's a decimal point, we can't start counting till we get to our first non-zero digit. So the first non-zero digit that we encounter is the number 7. So that's where we start our count. So that will be 1. The 9 will be 2. The next 9 will be 3. So that is the answer. Kind of a trick one, right? It already has 3 significant figures, the 7, the 9, and the 9. Trick here was to know that those first 2 zeros were not significant. So the next one, 5.027. 5 counts. This 0 counts because there's a decimal point and because it's between 2 non-zero numbers. And then this 2 will be our third significant figure. So let's look at the number next to it. Is it 5 or higher? It is. It's a 7. So we're going to round up to 5.03. Now the last one, save the hardest for last, right? So we have 0.001998. So when I start counting, I'm not going to start counting till I get to the 1, because that's my first non-zero number. All those zeros before it don't count as significant figures. So 1, then I got the 9, and then I got another 9. So that's 1, 2, 3 significant figures. Now I always need to look at the number next to it to see if it stays a 9 or if it's going to move up. And it does move up. Okay, so when a 9 moves up, that's going to change that 9 into a 0. Well, then we have another 9 after that, so that's going to move that up as well. So our answer for this one is tricky because we're rounding all the way to 0.002. I have to practice my writing with this thing. So the answer for this one is going to be 0.00200. So the 2 counts because that's our first non-zero number. And then the zeros after it count because we started counting at the 2 and there's a decimal point present. So that one's a little tricky. If you're having any troubles with that, make sure to ask some questions in class and we can do more like it. Now let's look at scientific notation. Scientific notation is basically exponential notation. So it's representing numbers to the power of 10. So 10 to the first, 10 to the second, 10 to the 10th. Right? It's just an easier way or a shorter way, not necessarily easier, to represent really large numbers or really small numbers. It keeps us from having to write all of those zeros that aren't significant. So here are just some examples. So 10 to the power of 1, or 10 to the first. Okay, all that is 10. They mean the same thing. 10 to the 0, that just means 1. 10 to the negative 1, that means 0.1. Okay, so some things that you're going to notice here is that if we have a positive exponent, like in this first example, 10 to the positive 1, the number is going to be greater than 1. When you have a negative exponent, down here, 10 to the negative 1, the number is going to be less than 1, in this case, 0.1. So negative exponents are going to be less than 1. Positive exponents are going to be greater than 1. And we're going to use this when we're going between normal notation and scientific notation. All right, so now let's look at how we're going to go from normal notation to scientific notation. So when I say normal notation, that's just going to be the original number, how we normally write it. We're going to apply these rules to figure out how to represent that normal notation number in scientific notation. So let's look at this example below. We have 29 million. Okay, so let's follow these rules to figure out how to get it in scientific notation. So the first rule says, let's have one significant figure to the left of the decimal. So when I'm rewriting this 29 million in scientific notation, I want to put my decimal point so that there's just one figure to the left. So that means it's going to go between the 2 and the 9. That's how I get this 2.9 right here. All right, well, how do I figure out the exponent? The exponent is going to be the number of times that you had to move the decimal point to get it where you wanted it. So what does that mean? I just said that in this problem here, I want the decimal point to be between the 2 and the 9. All right, well, how many places do I have to move the decimal point to get it there? I'm going to start at the end of the number and start moving this decimal until I get it between the 2 and the 9. So I have once, twice, 3 times, 4 times, 5 times, 6 times, 7 times. So I have to take that decimal at the end of the number and I'm going to have to move it 7 times to get it between the 2 and the 9. So that's how I get an exponent of 7. Now next we need to figure out if that exponent is going to be positive or negative. So one way to figure that out that we saw in the previous slides was if you have a number greater than 1, you're going to have a positive exponent. If you have a number less than 1, you're going to have a negative exponent. Well, in this case, 29 million, that's much, much greater than 1. So it's going to be a positive exponent. But another way that people like to remember it is that the exponent's going to be positive if you move the decimal to the left. So we started at the end of the number and we move the decimal point 7 times to the left. So that is why it is a positive exponent. Last but not least, only keep significant figures. So in this original number, 29 million, there were only 2 significant figures because just the 2 and the 9 count. All the zeros after that don't count because there is no decimal point. So let's do the next one. The next one is a very, very small number, 0.00003303. So we're going to start off by figuring out where we need our decimal point to be. And the first rule says that you want one significant figure to the left of the decimal. So we're going to put that decimal between the 3 and the 3. That gives us one non-zero number, in this case a 3, to the left of that decimal. All right, now let's figure out what the exponent's going to be. So the exponent's going to be the number of times you had to move the original decimal point to get it to where you want it. So the original decimal point this time is over here between these 2 zeros. So how many times do I have to move it to get it between those 2 3s? To move it 4 times to get it between those 2 3s. So that's why we have an exponent of 4. Now why is the exponent negative? Well, because the original number was less than 1. If your original number is less than 1, you're going to have a negative exponent. The other way to look at it is it's negative if you move to the right, which we did. We moved 4 times to the right. Then last but not least, check your sig figs. Okay, there's a decimal point, but we can't start counting till we get to our first non-zero number. So 3 is going to be our first significant figure. Then this 3 will be the second. That 0 counts because it's between 2 non-zero numbers and it's after the decimal point. So we have 4 significant figures. That means our answer should have 1, 2, 3, 4 significant figures, and it does. Going from a small number to scientific notation. So these next few slides are just some rules for you to look at through your own perusal to figure exactly how to go from small numbers and also from big, which I just showed you on the previous slide. So you can use these as just some extra practice. You'll notice for this one below, it is a number less than 1, so it has a negative exponent. We followed all the rules, keeping just one non-zero number to the left of the decimal and keeping our significant figures. This next one is a large number to scientific notation. So once again, following the rules, we have a positive exponent because the original number is much greater than 1. We kept our significant figures and we have just one non-zero number to the left of the decimal. Now, you're not only going to need to go from normal notation to scientific as shown on the previous slides, but if you are given a number in scientific notation, you need to be able to go back again to normal notation. So some things to remember is you want to always keep in mind significant figures. You want to move the decimal the number of places indicated by the exponent. You might need to add zeros, either at the end of the number or before the number, depending if it's a positive exponent or a negative exponent. If you have a positive exponent, you want to make sure to move to the right to make the number bigger, right? If I'm moving a decimal point to the right, I'm adding zeros, I'm making the number bigger. Positive exponents are numbers greater than 1, so that makes sense. If you have a negative exponent in the scientific notation form, you're moving the decimal point to the left, the other direction, making the number smaller. Negative exponents means smaller number, less than 1. Here are some examples that we're going to be doing in class. So all of these numbers are in normal notation. We're going to be representing them in scientific notation using the previous rules described. We'll also do some examples of scientific notation where we go to normal to practice the rules discussed. Calculator practice. So for this one, I just wanted to get people a chance to try out exponents on their calculator in case this is the first class that you've used exponents. So bring your calculators to class, work these out if you're having any problems. Depending upon the type of calculator, it could be the way you entered it or whether you're in different formats, so we can get that figured out during class time. If you are opting for online, make sure that you have a Zoom meeting with me or send me an email if you're having any troubles getting the correct answers. So you'll find these answers on the videos for in-class time. So all this slide is showing is just multiplication and division of exponents. Now you're going to be doing these in your calculator, so you probably won't be using this method. I just wanted to show a quick explanation because you'll see me use this method from time to time on the board, just so that you've seen it before. So when you are multiplying two numbers in scientific notation, you can simply add the exponents together, which is a nice little shorthand trick so you don't have to enter it into your calculator. So here we have 10 to the negative 27th and 10 to the positive 23rd. So those are our two exponents. So with the exponent portion of these numbers, we can just add the exponents together to get the final answer. And that's what's shown here. When we're doing division, instead of adding the exponents, you actually subtract them. So that's just the difference there. So you'll see me use this on the board, but as long as you're apt at using your calculator, you won't need to use this method at all. So this concludes the first part of Chapter 1. We will do a short review of these different topics in class, as well as several practice problems on the board. Let me know if you have any questions.